Hey guys, welcome to Chapter 3. It's titled Mass Relationships in Chemical Reactions. We're going to use everything that we've learned about the chemical structure, like protons, neutrons, isotopes, and formulas in studying the mass relationships of atoms and molecules. These relationships are going to help you understand and explain the composition of compounds. Okay, let's get started. In Chapter 2, we learned about isotopes, and we learned that an isotope is something that has a different number of neutrons. Now, take that information, and I'm showing you here 3 isotopes of carbon, carbon-12, carbon-13, and carbon-14. And I ask you a very simple question. Do you think if you were to hold a sample of carbon, how much of each isotope would you have? Would you have a third of each? As a matter of fact, you will not have a third of each. I'm going to introduce a term that's called percent abundance. And we're going to learn percent abundance and how to do math problems later in this chapter. But for right now, I just want to tell you that the percent abundance of each isotope of carbon is not 33%. As a matter of fact, it's 99% carbon-12, 1% carbon-13, and a small tiny amount of carbon-14, which is a radioactive compound. So if you were to hold a sample of carbon in your hand, this would be the ratio that you would have. To drive this point home, I want to give you another example. So let's say I have 100 carbon atoms, all mass 12, and I have 113 that you see there. If I was to cover up that 13 and I asked you, okay, now we have all these 12s, what's the average? If I took the average of all these numbers, what would the average be? You would say 12 because they're all 12. But now I take away the cover and I show you, okay, wait, now there's a 13. And I say, let's take an average of all these atoms now. What would you tell me the average? Would the average go up or would the average go down? Well, the average would go a little bit up because you have that 113. Now, I want you to go to the front cover of your book and tell me what is the mass that you see for carbon. The mass is 12.01. Why do you think that is? It's because the masses that you see in the periodic table are an average of all the isotopes for that given element. So since there's 99% carbon-12 and there's 1% carbon-13, they take the average of those, and that's how they figure out the mass that you see in the periodic table. And that, of course, goes for every single element. So the average atomic mass is the average mass of all the naturally occurring isotopes of an element. The figure on the left shows what you would see in the front cover of your book. So if you look, carbon has 12.01 atomic mass. What you see on the right is from another chemistry book, which you can see is a little bit more accurate. It has more significant figures. So if I was to ask you what the mass of oxygen is, you would say 15.994. In your book, if you look, oxygen is 16. This one's a little bit more, accurate, a little bit more precise, but why do you think it's 15.994? It must be that one of the naturally occurring isotopes of oxygen is a little bit less than 16, which brings the average down. So we keep talking about atomic mass, and we say that 12.01 is the atomic mass of carbon, but you know how I'm big on units. So it's 12.01 what? What are the units of atomic mass? The unit for atomic mass is atomic mass units. Isn't that pretty simple? So carbon, for example, is 12.01 AMU, or 12.01 atomic mass units. So how much is this in grams? If you wanted to express it in grams, how much is it? Well, there's your conversion. 1 AMU is equal to 1.661 times 10 to the negative 24th grams. You don't need to memorize that, but if you were given a question, you could use this conversion to help you convert between AMUs and grams. So now that we know what atomic mass and the units are of atomic mass, let's talk about molecular mass. If I wanted to know the mass of carbon, we know that all we need to do is look at the periodic table. It's 12.01 AMU. But what if I wanted to know the molecular mass, right? The mass of a molecule. What would I do? Well, simply enough, I would go to each and every element and add those elements up. So if I had, let's say, carbon monoxide, which is 1 carbon, 1 oxygen, I would take the atomic mass unit of carbon, which is 12.01, and the atomic mass unit of oxygen, which is 16, add those together and get my molecular mass for that molecule. The official definition of molecular mass is sum of the atomic masses of the elements in a chemical formula. So if I wanted to know the molecular mass of oxygen, or O2, one of the diatomic molecules, all I would have to do is take 2 oxygens, which they're both worth 16 AMU, and add them together. So 16 plus 16 is 32 AMU. The same goes for any other molecule. If I was to ask you what the molecular mass of that molecule is, all you gotta do is add everything up. And also the same goes for ionic masses. All it is just a different name. If I wanted the ionic mass of an ion, all you got to do is add up all of those atoms that make up that ion and give me the mass. It's just we use different names for the type of compounds they are. But it's the same thing always. You just add everything up and you give the total. Okay, now we're going to start learning about relative masses as well as the mole. So we just learned a couple minutes ago that the masses that you see in a periodic table are the average atomic mass of all of the naturally occurring isotopes. Now, what I'm going to tell you is that if you were to get 4 grams of helium, right, because that's the atomic mass of helium, and 20 grams of neon, you would have the same number of particles of each of those atoms. Even though one is 4 grams and the other one is 20 grams, you're going to have the same number of particles. The reason that is because all of those masses that you see are relative masses. So if you took 4 grams of helium and you took 20 grams of neon, you would get the same number of atoms, particles, whatever you want to call it. That number of atoms or particles that you get is 6.02 times 10 to the 23rd. How did we do that? What we did is we took the atomic masses and expressed them in units of atoms, and all of them come out to 6.02 times 10 to the 23rd. So how do we get this magical number? Well, if we were to take 4 grams of helium and we knew how much 1 atom of helium weighed, which we know, of course, it's 6.64 times 10 to the negative 24th grams. If we divided that atomic mass by the grams, the mass of 1 helium atom, guess what we get? 6.02 times 10 to the 23rd helium atoms. Now, let's do something else instead of neon. Let's try iron. The atomic mass unit of iron is 85.45. If I divided that by the mass of 1 iron atom, guess what? I'd come up with the same number. That's 6.02 times 10 to the 23rd. That is called Avogadro's number. We're going to be using this all throughout the semester. This is a way that you can get from atoms to moles, moles to atoms, moles to particles, so on and so forth. Avogadro's number, I want to stress, is just a number. 6.02 times 10 to the 23rd. It is also referred to as the mole. If you have 1 mole of something, you have 6.02 times 10 to the 23rd of that something. So let's say I want to know how many desks are in 1 mole of desks. Guess what? I have 6.02 times 10 to the 23rd desks. It's a lot of desks. All right, so we're going to talk about that more in the second video. I'll see you then.